Okay, talk a little bit about what we do at NASA and why we need multi-rail routing for Luster. Okay. So if it's cool, we're doing it at NASA, right? So, I mean, rocket science, of course. We're building a new launch vehicle, SLS. So this is kind of a capacity problem, right? So you're doing lots of simulations of, say, a launch abort system. So the new rocket's going to have a way for astronauts to get off if the vehicle has a problem on ascent. So things of this nature, a lot of aeronautics work. Space and earth science, ocean modeling, galaxy formation, these sorts of things. They're more large-scale capability type problems. And then there's a class of time-critical type applications. So in the news recently, you probably heard of TESS. We're going to be, it's an exoplanet mission where we're taking pictures of stars. It's a spacecraft that's circling out to the orbit of the moon and coming back and then transmitting the pictures that it took, and then we're going to be processing that on Pleiades on basically a monthly basis for the next several years. Reentry analysis, storm prediction, these sorts of things are kind of time critical. So the group, this is HECC project. This is the project I work under, and I have supercomputing systems. So I'm the lead system architect for that and lead for the systems group. And so we provision all of the infrastructure for the supercomputing that's done at our facility. These are basically just a list of the platforms. You may have heard of Pleiades. It's our biggest system in our classic facility. Electra consists of 2 prototype systems that we're building, which are a modular facility installation. I'll talk a little bit about that. Several Luster file systems, NFS file systems, and we have a BGFS file system that I'm working on. About 40 petabytes of data, 500 petabytes on our tape archive. So it's not maybe as large as a DOE lab, but it's a fairly substantial installation. So here's our growth over years. If you just measure our LINPACK number, Pleiades came in here about 2008. And so I think the takeaway from this chart is that we're continually updating the system. So we're adding equipment in, retiring equipment, and sort of scaling that over time. So we're constantly turning over new equipment in there. And about this point in time, we ran out of power. So that's about what you get for 6 megawatts at that time frame when you have figure in cooling. And so at that point, our facility wouldn't let us grow anymore, and so we're trying to figure out ways to add power. We have plenty of power, we just don't have a way to cool it. And so these growth projections down here were from a system we call Electra. Traditional computer facility space. These are our computer floors where things sit, and it's largely up to this point been classic water towers with chillers that you run, and we get PUE ranging from 1.5 on our oldest systems to the main floor where Pleiades is, we get about 1.3, and that's not bad for that style of system, but it's still pretty high. So we've built 2 modular test beds. They sit in the parking lot across from our main building over here, and these are modular computers that are space purpose built buildings that drive PUE down to about 1.04. There's 2 different types of those kinds of facilities. This is all air, and this is primarily water and self-contained. And so the advantage here is that we get about double the density, and we can drive things like GPU or Xeon Phi or those sorts of configurations in that facility and cool it with ambient air, so no compressors involved. Here's a picture of that first Electra module here, and sort of a design of what it looks like inside. That's a fancy graphic, sort of shows you, you know, the air comes in from the outside, goes in here, hot alley ejection. There's swamp coolers on the ends. So in our area, this is quite efficient from power and cooling. So this is actually the second module and a little video time lapse of it coming in and being built. And you can see the day to night transition over the period of, you know, a little, you know, around a week or so. You have this prefab facility that comes in, assemble it, put chillers on the top, which are dry air coolers, add about a megawatt of capacity, and that second module will hold on the order of 2,500 nodes. So this is the concept that we're using to expand the facility beyond our current limits. So we'll go to the next one. So the full site deployment this is just a cartoon of, you know, what that might look like, but you can imagine bringing in several of these modules, staging them in as we, you know, have funding or need, and of course we're going to need routing and Luster routers to get to that equipment, and see, because it's physically, you know, this is where 258, these are where the two prototypes are, and then our new facility site location. And so that's, we're provisioning up to 30 megawatts of power there, but it'll all be at that, you know, 1.04, 1.03 sort of PUE number. So our motivation is, you know, that the facilities that we're building, they're physically distributed. And so we need to figure out ways to provision lots of bandwidth, you know, order hundreds of gigabytes to, you know, terabytes a second in a cost-effective way. And so we want to maximize utilization of the servers that we have. Laying fiber in the ground is really cheap, but getting it to all the components where it needs to can be, you know, that last 10 feet can be expensive. Our procurement strategy is we typically buy yearly as funds become available, and so that results in this incremental grow. We may time, you know, based on processor network availability, but it results in several incremental smaller builds. And so we use thin provisioning too for a lot of our non-compute elements, and that in particular, that's storage. And so that's a nice way to say, you know, we beat the crap out of our storage systems to prove to ourselves that we need to update them. Because it's not always hardware, you know, a lot of times it's software and Luster or other things that users are doing, and throwing hardware at it may not really solve the problem. Future system, building in multiple phases. We've completed 2 prototypes. We're actually building out that final NFE deployment area, which involves bringing in power, pouring a concrete pad, and preparing for equipment that'll show up probably early next fiscal year. And the networking designs, we really, you know, you need them to be performant and redundant, and ideally active-active. And so, overview of this is what the Pleiades system looks like. Because we're incrementally growing these systems out, we like hypercubes because that kind of allows us to grow them in any dimension that we want. And so there's 2 fabrics. Each node connects to both fabrics, and each of the little red dots here is actually a 36-port, you know, InfiniBand switch. And so off of those, each of those elements, you've got 9 compute nodes. So then something that we did was modify the standard DOR algorithm to do weighting to allow us to build an external switch fabric that we connect all of our I/O elements to. And that's depicted here in this, which is a 3D torus. And so we can route that as a hypercube with those weighting algorithms. And then this is where all of the Luster components are connected, and we have additional cabling going to the primary IB1 network and a hyperwall viz system, and you know, the switching for that downstairs. So the task here is to connect our primary I/O infrastructure on Pleiades to these modular buildings that sit out in our parking lots in a way that's performant and transparent to the users. So Electra, just a smaller version of Pleiades. It's an 8D hypercube. The first system had 1,100 nodes, same design, 9 nodes per vertice. And this is where, the LNet routing came in with multi-rail. And so our first initial take on this was we're using MetroX. This is actually across the parking lot, so that's a couple hundred meters. We're using 8 LNet routers across the MetroX and then tying that into our Pleiades I/O fabric. And then talking to Amir at one of the Open Fabric workshops, our real desire was to have an active pair of these LNet routers actually use Connect IB, so they're by 16 PCI 2-port cards, so we can drive 16 gig, over PCI on both sides, and with 2 ports of FDR, then we can get to, 12 or so gigabytes, 11 gigabytes a second potentially, but no way to do that in LNet. So Amir and I talked, and he says, "I think I can do it, Bob." And so he actually went and figured out how that we could, without actually having multi-rail aware clients or servers, to just run the multi-rail components on the routers themselves. So this was sort of a hybrid installation, and what we got then out of that was a way that all of the compute nodes over here effectively round robin over all of the router interfaces. And so then we extended that, doubled that. That's version 2 of that module, where we have now 2 groups of 1,100 nodes of compute out there with this multi-rail configuration. And so they all now can round robin and effectively get all of the bandwidth that's available to those networks. And then since each of these LNet routers are connected twice to all of the 16 routers that sit in our 3D Torus I/O infrastructure, then they get really good load balancing across all of our other Lustre components that sit in the main building. And so the next phase of that is, again, to double Electra. So we'll have about 3,500 nodes over there, about 1.5 megawatts worth of compute. And so that's about the approximate footprint of each of the modules that go into our new facility. Here's a little bit about what the router configuration was. We have 15 routers. We do 1 IP router. There are the Connect IB cards and Lustre versions and things there if you're interested. Just a little bit cleaner overlay of what actually the connections were and performance results. So for reads, you can see the single rail numbers are in orange or red, and the lime green here for multi-rail, and so the scalability is quite good. On the read side, so we're getting over 100 gigs. And so on the right side, we get quite a bit better, but we see this tail right here, and so this is, an issue with the way that the routing is done on the modules themselves. And so when you do client placement, what we really want is a routing algorithm that gives us good load balancing over all of the rotors that we're using for the LNet targets. And so there's some work we're doing with Mellanox with routing chains in order to improve this. And so this was really just a 54 client test. So out of the 2,000 or 2,200 nodes that are out, that is a pretty small section. If you grow it, we get a little bit better scalability, but that's kind of, it is what it is right now. Aggregate numbers for read-write test, hitting up to 160. So I think that's, a design goal met. So we get good load balancing. We can take down routers, update them. Both, switch pair can fail, routers can fail, and it's all, the compute system's all right through that. So I think that's real successful. implementation for what we want to do with this sort of distributed campus area infrastructure. So here's a layout for what the LNet options are. Take a look at those. And specific thanks to the Intel team and Amir. And these are, the people on my team that worked on it. And Amir's going to speak some to give you some more details of what that is.
What we configured, because I think it might be useful for other sites as well. So the requirements, just to reiterate a little bit, is we wanted to connect 2 segments of the cluster via routers. The routers have dual, like 4 interfaces, 2 interfaces facing each side. And we wanted to aggregate the performance of the routers, but have router resiliency as well, which we won't have right now with multi-rail because that's coming in later. And we wanted to keep the clients and the servers both non-MR. So again, just this is a more generic kind of connection. So the purpose of the configuration was to try to achieve this requirement. So what we did is we configured each router interface as a different gateway. This way, the clients and the servers see the 2 interfaces of the routers as 2 separate gateways. And we already have code in LNet to handle router failures. So if one interface goes down for whatever reason, then the other interface, then the router code will switch to the other gateway and start using the other interface. The clients and the servers were not configured, didn't know about multi-rail in the first place, so they dealt with each interface as a separate peer. And the routers, there's one trick that we used in order to balance the traffic. Routers we had to trick the routers to tell it that the peers, which are really not multi-rail capable, are multi-rail capable. The reason we did that is because the code when it selects the interface it should send from, if it detects that the other side is not multi-rail capable, then it will only use one of the interfaces to avoid confusing it. But in case of routers, that's pertinent for if there's actual client to server communication. But because routers, it doesn't really matter. Routers are just routing the traffic. So we could do that. We can trick the routers to tell it that the other side is multi-rail capable, and then we'll just start round robining over both interfaces. Therefore, we aggregate the traffic. So this is the configuration that Bob showed. In a little bit to make it more generic, on the router we configure the 2, the 4 interfaces or however many interfaces, 2 on one network and 2 on another network. And then we tell it about the clients that they are multi-rail capable. That's the trick that I told you about. And we set the routing. And then on each of the client servers, same thing, we create the network. That's the first line. And then after that, we add each interface of the same router as a different route entry in the routing table. And this way, when the client starts sending traffic, it will just round robin over those 2 those 2 gateways from its perspective, but it's really just 2 interfaces of the same network. Of the same router. So advantages of that is we can leverage the router checker code that's already there to monitor both router interfaces, and if one goes down, we can just switch to the healthy one. And again, we aggregate the performance because you go round robin over both interfaces, so you use all the bandwidth that's available to you per router. And again, I just repeated the trick that we used to trick the routers into using both of its interfaces. And this approach works for both mixed, in NASA's case, mixed MR and non-MR clusters. One thing I want to point out, there is an ARP issue that if you do configure, if you have multiple interfaces on a peer, on a node, you have to kind of fiddle around with the Linux routing a little bit, because what we found is that if you try to ARP a specific interface, the address that comes back sometimes is for the wrong interface, and that confuses the connection, like it prevents a connection from being set up. So there is some sort of fiddling and configuration that we had to do in order to get the Linux routing to return the correct hardware address in the ARP. And that's documented in this link so that people can find it easily. So in conclusion, the cluster doesn't need to be fully MR capable to gain the MR advantages. And we can increase router performance as in case, and at the same time have the resiliency that's needed. And that's it. Thank you. Questions?
Failover in the MR only between two interfaces, or can multiple interfaces fail over and multiple LNet routers fail over?
Have to, you don't, like, it can be an arbitrary number of interfaces that you have there, and you can just like fail over each one, because we select the multi-rail according to each one. Yeah.
More question? No.
Hi, maybe I just don't get it, but the trick you used into having routers think that they were really multi-rail capable, but the other parts of the network did not have to believe that they were multi-rail capable. I'm having a hard time grasping how that works. In a nutshell, I mean, I'm sure it's complex, but I just don't even see how that works.
Not complex. It's basically you configure each router, right, with the other peer's interfaces, and you say that peer is multi-rail. But by configuring the peer's interfaces, you tell the router that the other peer is multi-rail capable. That's just how the configuration works. The algorithm that selects like round robins over the different interfaces of the peer, right, and the local interfaces, it needs to know that the peer that it's talking to is multi-rail capable in order to round robin over its local interfaces. If it figures that the other side is not multi-rail capable, there's a risk of confusing it, so it doesn't use it. It keeps using only the same interface always. So we needed to add that trick to make it use both interfaces, the local interfaces, if that makes sense. Sorry if the description is not great.
Multi-rail thing to an endpoint. That the endpoints obviously do not have that, because that would indeed induce the confusion.
Yes, yes. So the clients and the servers are not, they have older Lustre versions that are not multi-rail available anyway, right? So you can't tell it that the router is multi-rail capable. Only the routers are multi-rail capable. So that's where the trick comes in.
Then in 212 is where the health check will be in place, so that you'll get the failover within the context of multi-rail, which is when, we're interested in multi-rail on clients and servers, but not until we get that resiliency piece put in.